evening, everyone, and thank you for joining. My name is Baiju Political, and I am a solutions architect with Cisco Systems, part of the Advanced Services Organization. Today and tomorrow, I would be covering IPv6 technology overview at a high level. The entire tutorial has been divided into two sections. Part 1 we will cover today, and tomorrow around the same time here we will cover part 2. Let's take a look at the agenda here. In tutorial section 1, we will start with the basics, looking at the structure of IPv6 protocol, followed by details of IPv6 addressing, and also we will take a look at ICMP-v6, the version of ICMP which supports IPv6, and also the relevance of neighbor discovery mechanism for the IPv6 protocol implementation. And towards the end of the session, we will take a look at DHCP as well as DNS at high level as pertaining to IPv6. Tomorrow, we will continue with tutorial 2, which would cover primarily the routing protocols for IPv6, both IGP as well as the EGP. And also we will take a look at some of the IPv6 transition mechanisms. Now let's start with the taking a look at the structure of the IPv6 protocol. I know most of you know that from the addressing perspective, the primary difference between IPv4 address and the IPv6 address is in the IPv4 world we used to have 32-bit address space, and in IPv6 is 128 bits. And let's take a comparison between the IPv4 header and IPv6 header. So as far as the base header itself is concerned, the size has been increased from 20 bytes to 40 bytes. However, we know that in the IPv4 world, an IPv4 header can vary in size anywhere from 20 to 60 bytes, whether there are options in the header or not, even though options are not usually used. In the case of IPv6 header, the header size is always fixed at 40 bytes. And in IPv6 also, the options are supported, but a different mechanism is used. Instead of using the base header itself for options and make it variable, something called extension headers are used in IPv6 to support various options such as source routing. And let's take a look at the different fields in IPv4 and IPv6. What you see highlighted in orange are retained as it is in IPv6. The version field still retained, and the version will indicate its version 6 in the case of IPv6. And as far as the source and destination addresses are concerned, those fields are as expected retained and with the same name. However, the difference here is the source address field and destination address field in the case of IPv4 only takes a total of 8 bytes, but in the case of IPv6 it's 32 bytes. Now let us take a look at some of the fields which are retained but renamed to make it more meaningful for the function it does. The type of service field, which all of us are familiar in the IPv4, which is used for implementation of quality of service, has been renamed as traffic class. It does the same purpose, it has got the same length, it also, it still supports the DHCP, and however, the name has been changed from type of service to traffic class. And the next field which is retained but the name is changed is the length, total length. In the case of IPv4, the total length field, which is 16 bits, covers the header as well as the payload portion of the IPv4 packet, mainly because of the fact that IPv4 header size could be varying anywhere from 20 to 60 bytes. So you need to have the total length section covering the IPv4 header as well as the payload. In the case of IPv6, the payload, the field has been replaced, and the name of the field has been replaced as payload length, just to highlight the fact that in IPv6 it only covers the length of the payload, not the header itself. What that means is, if you have extension headers following the IPv6 header before getting into the higher layer protocol headers, it will include the extension headers as well. We will see a little more detail about the extension header in subsequent slides. And moving on to the next field, which is retained, but the name has been changed. The time to live, all of us know in the IPv4 world, even though the field is called time to live, it actually indicates how many hops a packet can traverse before it has to reach the destination or it gets discarded, right? So to reflect the actual function performed by the time to live field, it has been renamed as hop limit. And finally, the protocol field is still out there because we need to have a field to identify what kind of higher layer protocol field is following the IPv6 header. However, in the case of IPv6, it is renamed as next header just to indicate that the next header could be either pointing to one or more extension headers if you have extension headers following the basic header, or it could be pointing to a next layer protocol such as TCP, UDP, or ICMPv6. Now let us take a look at some of the fields which is removed in IPv6, which was out there in IPv4. Header length, which was out there in IPv4, is no longer required in IPv6. Right, because of the fact that in IPv4 we have a variable length header which can vary from 20 to 60 bytes, but in IPv6 it is a fixed length 40 bytes header. And identification flags and fragment offset fields, as you know, are relevant when you implement fragmentation functionality. If by any chance, if you want to send packets, right, which are larger than what is supported by the path MTU from source to destination, either the source itself or intermediate routers along the path could be performing fragmentation in the case of IPv4 implementation. And if fragmentation is done, then you would need to have the corresponding fields, identification flags, and the fragment offset so that at the destination side, the packets can be reassembled. However, in IPv6, the fragmentation is supported but handled in an altogether different way. In IPv6, the intermediate routers, which does the IPv6 routing, does not do any kind of fragmentation. Always the sending IPv6 node is expected to do a path MTU discovery from source to destination and either send the packets at the lowest MTU along the path, or if it has got IPv6 packets which is larger than what is supported by the lowest path MTU, then it has to implement fragmentation, fragment the packets at the source node itself. The routers, the intermediate nodes in IPv6 network does not support fragmentation. And the fragmentation in IPv6 is implemented by making use of an extension header. Because of that, you don't need those fields, identification flags and fragment offset, as part of the base IPv6 header itself. And as far as the header checksum is concerned, the primary reason the header checksum is removed is today we know that almost all data link layer protocols out there supports error checking mechanisms, sophisticated error checking mechanisms. So it makes it quite redundant for you to do an error checking for the IPv4 header as well. So it is removed for IPv6. And options and padding does not make any sense because the header is not of variable length. The way we support options is by making use of extension headers. And there is a new field which is introduced in IPv6 which is called flow label, as you can see, which is grayed out here. The flow label is used for implementing enhanced QoS mechanisms for specific traffic flows. The flows are identified in IPv4 typically as the source address, destination address, the protocol, the source port, as well as the destination port corresponding to TCP or UDP. So instead of using this set of 5 parameters to uniquely identify a flow, in the case of IPv6, the source nodes have got the option to assign a flow label to a specific flow from a specific source to a destination and corresponding to an application, so that intermediate routing nodes, if it has been configured to support enhanced QoS, can be treating the packets with the configured QoS based upon the flow label parameter. However, this is not commonly implemented today. So if the flow label is not in use, typically the sources would set the value to 0. Now moving on to extension headers. As I mentioned earlier, if you have one or more extension headers following the IPv6 base header, the next header field would be indicating that it is an extension header. So there are different values defined for different extension headers, and the next header value will indicate what kind of extension header is following the base header. And there can be n number of extension headers following a base header. So in each extension header, as you can see, there is a next header field in the header for the extension header, right? So the next header field in the extension header could be pointing to either an upper layer protocol or another extension header, depending upon the implementation. So all what it says is you can cascade multiple extension headers in order to support multiple IPv6 options before it gets to the upper layer protocol header. These are the list of some of the extension headers. So you have two kinds of extension headers generally out there: hop by hop extension headers and destination options header. The hop by hop extension headers are processed by every intermediate router as well as the destination. But extension headers which are categorized as destination options header are processed only by either the destination node, typically the destination node. However, the exception would be if you have source routing enabled. The source routing is implemented in such a way that every node, when it processes the source routing enabled packet, it would change the destination to the next routing node which needs to handle the packet. Finally, it will keep changing it, and the last hop router would be changing the destination address to the destination of the end node itself. So if source routing is enabled, then the destination options header would be processed by the intermediate nodes as well. So depending upon the type of the extension header, if you have multiple extension headers, there is a sequence in which these extension headers need to appear as well. So it has to follow this particular sequence because some of the extension headers needs to be processed prior to processing the other extension headers. I know we talked a little bit about MTU, and we know that fragmentation and reassembly is supported in IPv6 as well, but IPv6 routers, the intermediate nodes, do not support fragmentation and reassembly. The minimum MTU size required for IPv6 implementation is 1280 bytes. Any IPv6 implementation is expected to support 1280 bytes. If any IPv6 node wants to transmit a packet which is larger than 1280 bytes, then it has to implement the path MTU discovery mechanism to find out what is the lowest path MTU supported between the source and the destination. However, if it is possible for some of the IPv6 implementations to not have the path MTU support out there in place, as long as it makes sure that the IPv6 packets are either 1280 bytes or smaller in size. And we do know that the payload length field has got a size of 16 bits. What that means is the typically the IPv6 payload can be as long as 64 kilobytes, right? However, if you want to have support for jumbograms, anything larger than what is supported by the field, which only supports 64 kilobytes, there is something called a jumbograms extension header option, which supports payload size as large as 2 to the power of 32. Any questions so far? Now let's look at the details of the IPv6 addressing. we all know that as far as the size of the IPv6 address is concerned, it is 4 times more, right, compared to IPv4. IPv4 address was 32 bits long, and in IPv6 we have a 128-bit address space. And what that tells us is the address space supported is much larger compared to the IPv4, right? And one of the reasons why everybody is pushing towards IPv6 is the depletion of the IPv4 address space itself. In IPv4, we theoretically had a total of slightly over 4 billion addresses supported by the 2 to the power of 32 address space, but in IPv6 it is kind of hard to imagine, but it's an extraordinarily high number. It is 79 trillion times the existing IPv4 address space. So just to get some idea, we know that we have around close to 6.5 billion people in this world, right? So every individual can be allocated with 52 trillion IPv6 addresses by making use of the address space. So the addressing format is different. In IPv4 world, we have a very user-friendly addressing format, which is the dotted decimal notation. In IPv6, we use something called a colon hexadecimal notation. The 128-bit address is divided into blocks of 16 bits. Each of them are represented in hexadecimal and separated by columns. And in order to make the handling easier, there are some abbreviations possible. If you have contiguous zeros which appear in an address, all of them can be replaced by a double column. However, you have to keep in mind that if there are 2 sets of contiguous zeros which appear in a single IPv6 address, only one set you can replace with a double column. The reason being, even though you are representing these addresses as hexadecimal and the abbreviated forms, end of day, the computers are going to deal with them. Computers and routers are going to deal with them as bits, right? And the way the computers are going to deal with the abbreviated address spaces, if you have a column, it can fill in as many zeros as required to take it back to 128 bits length. But if you have 2 sets of zeros, and if you replace both of them with 2 column, then it's hard to find out how many zeros are required to fill in the first column, and how many are out there to refill for the second column. So the column can only appear once to abbreviate all the contiguous zeros. And the leading zeros in any of the 4 nibble blocks can be omitted without losing the meaning of the address. As you can see, instead of 0 db8, you can always say 2001 column db8. However, the trailing zeros cannot be omitted. It will change the meaning of the address. The prefix representation is something similar to what we have in IPv4 for classless inter-domain routing. For example, if it is instead of class B representation, we use the /16 to tell that the first 16 bits represent the subnet ID or the prefix, and the remaining 16 bits in the case of IPv4 is the host ID portion, right? Likewise, in V6, here, by using /48, it indicates that this represents a prefix, and the first 48 bits of the address space represents the prefix or network ID portion, and the remaining bits represent the host ID portion. And in this case also, when it comes to the representation of the prefixes as well, you can always omit the leading zeros to abbreviate the address. These are some of the special addresses out there in IPv6, like the 127.0.0.1 internal loopback address, which we have in IPv4. There is a similar address defined for IPv6 as well. It is column 1, or all 0 followed by 1 being the last bit. And if a node has not been assigned with an address, Any unspecified address, we know that in IPv4 is represented as 0.0.0.0, and in IPv6 it is represented as all zeros, and it can be abbreviated as colon. This colon or unspecified address is particularly useful for DHCP interactions when a node has not been assigned with an address, and also for duplicate address detection mechanism, which we will see later in the session. The IPv6 address has got scopes. Like we know that in the case of IPv4, we have two categories of addresses, right? Globally routable IPv4 addresses, which are assigned by the regional NICs, in turn which are received from the INA, and then there are private address space represented by the RFC 1918 spec out there, which primarily consists of the 10net, 192, 168 as well as 172.16 address space out there. Likewise, the IPv6 addresses also have got scopes. There are three scopes out there defined for the IPv6 addresses. The global scope, which represents any of the address space which is assigned by INA and the various regional NICs, and then the unique local address, which is similar to the private address space what we have in the IPv4. The unique local addresses are addresses which can be used in a enterprise network or providers networks, but it is not supposed to be showing up in the global routing table. Then you have the link local addresses. Link local addresses are used primarily for IPv6 control functions. Every individual IPv6 node must support link local addresses. Link local addresses are used for some of the link layer functions, and link local addresses are never routed by any of the IPv6 routing nodes. It only has got scope within a layer 2 local domain. And addresses are generally assigned with lifetimes. Two lifetimes are out there: the valid lifetime and preferred lifetime, which is typically useful when automatic address assignment is used. From the prefixes, you can tell what kind of address an IPv6 address is. The globally assigned unicast address always starts with 001. The first 3 bits out of the 128 bits for the globally assigned unicast address would always be 001. Because of that, the globally assigned unicast address always start with the hex digit either 2 or 3. The link local unicast address has been provided with the standard prefix FE80::10. Any address which starts with the prefix FE80::10 is a link local address. And then the unique local unicast address has been assigned with the prefix FC00:7. Again, FC00:7 is further divided into FZ00:8 and FD00:8. As you know, because when you flip the bit, the last bit, it becomes either C or D, right? Depending upon whether it is 0 or 1. FD00:8 is what is used by enterprise and service providers for any kind of private addressing, because FC00:8 is right now reserved. It is supposed to be assigned by some kind of authority, either the INA itself or in some mechanism to make sure that there is some level of uniqueness even for this administratively scoped address space. And finally, the multicast address space is represented by the prefix FF00:8. Anything which starts with FF represents a multicast IPv6 address. And there is no such thing as broadcast out there in IPv6 world. So there is no broadcast equivalent of an IPv4 address for IPv6. Moving on to different types of IPv6 addresses. Unicast, as all of you know, right? It represents a single interface, address of a single interface. And then you have the multicast, right? Represents multiple interfaces. And there is something called an anycast addressing also order, which is we have that in IPv4 as well. As far as anycast is addressed, it represents one-to-one of many delivery, primarily used for locating the services. And as I mentioned earlier, there are no more broadcast addresses in IPv6. Now let us take a look at the global unicast address. As I mentioned, the global unicast addresses starts with either hex 2 or 3, because the first 3 bits are always constant, 0, 0, 1. And then followed by that, you have something called a global routing prefix, which makes it a total 48 bits, representing typically the service provider. And then you have a subnet ID, which is 16 bits. And then finally, you have the remaining 64 bits identified as interface ID. And this is the unique local address format. Here the 7 bits are constant, which is FC00 column /7, and we know that that again is divided into FC00 column /8 and FD00 column /8. The global ID, the 40 bits space here, can be either randomly generated or manually assigned, which is up to the administrators of the network, how they want to generate the global ID. Then you have a subnet ID portion available, which is 16 bits long, for identifying different networks within your enterprise, right? And then finally, the interface ID, which is 64-bit, represents the host portion. The host portion is typically represented by a 64-bit interface ID. Similar to IPv4 world, the unique local addresses are used for local communications, industry-side VPNs, etc. And as I mentioned earlier, these are not supposed to show up in the global routing tables. Moving on to link local addresses, we have seen that FE80 ::/10 is the prefix reserved for the link local addresses. And you have remaining 54 bits out there for the network ID portion, and then you have the host or interface ID, which is 64 bits, right? These 54 bits can be any value, but so far the implementations, IPv6 implementations out there, have been using all 0 for these remaining 54 bits. So effectively, FE80 ::/10 becomes FE80 ::/64 prefix for link local addresses. Then you only need to build the interface ID portion. Link local addresses, as I mentioned, is used for many IPv6 control functions, such as link layer address resolution, duplicate address detection, router discovery, etc. And also most of the IPv6 routing protocols extensively use link local addresses for sending and receiving the routing updates and other routing control packets, as well as the next hop for the routing protocols. Moving on to the IPv6 multicast address, we know that FF represents a multicast IPv6 address, which is 8 bits, right? And remaining 8 bits represents the lifetime and the scope. So the addresses can be either permanent or temporary, depending upon what is the setting of one of the bits in this nibble. And then there is a scope which tells what is the scope of the multicast address. Whether the node local scope means a multicast address can never leave a single node. The link local scope means the multicast address cannot leave that particular link or layer 2 domain. Then you have the site local scope, organizational local scope, and global scope. Any multicast address which has got the global scope can be globally routable, right? And will be globally assigned address. The site and organizational scopes will actually depend upon the boundaries of the site, and organization scope will actually depend upon the administrators. But however, you have 2 different scopes out there for administratively defined boundaries for multicast. One is number 5, which represents the site local scope, and 8, which represents the organizational local scope. This is a list of some of the well-known multicast addresses. FF01 column 1 is an all nodes multicast address, but the scope is limited to a single node. Then you have FF02 column 1, which has got link local scope, which represents all the nodes, because the 2 indicates that it has got link local scope. FF01 column 2 is a node local address representing all the routers. Then you have FF02 column 2, which is a link local address which represents all routers. FF02 column 1 and FF02 column 2 you would see more when we discuss the neighbor discovery portion of the ICMPv6. And finally, there is an important IPv6 multicast address called solicited node multicast address. Every unicast and anycast address has got a corresponding solicited node multicast address. For now, here this is the prefix which is defined for the solicited node multicast address. And the solicited node multicast address is created by making use of this prefix and filling the remaining 24 bits here with the lowermost 24 bits of a unicast or anycast address. This is very, very important for neighbor discovery mechanisms, link layer address resolution, duplicate address detection, etc. We do know that in the case of IPv4, we have a mechanism out there to map the IPv4 multicast addresses to Ethernet group MAC addresses, right? Likewise, there is a mechanism defined in IPv6 also to map IPv6 multicast addresses to corresponding Ethernet addresses. It is very simple and straightforward. All what you have to do is take the lowermost 32 bits of the IPv6 multicast address and append the constant value 3333, making it the 48 bits Ethernet multicast MAC address. Now moving on to solicited node multicast address, as I mentioned earlier, solicited node multicast address plays an important role in neighbor discovery functions. And the way the solicited node multicast is created is by making use of the solicited node multicast prefix, which is a constant, and by adding the lower 24 bits from the IPv6 unicast interface ID. I think the next slide shows an example. Here we have a link local unicast address. How are you saying this is a link local unicast address? Because we can tell by looking at the prefix, right? FEAT always tells that the address is a link local address. So what you have here is a 128-bit link local unicast address with a 64-bit network ID portion and a 64-bit interface ID portion or host ID portion. And then we have the solicited node multicast prefix, which is FF02 column 1 colon FF, right? And what is missing for the prefix is the lowermost 24 bits. So it maps the lowest 24 bits of the unicast address into the multicast address, thereby giving you the full 128-bit solicited node multicast address. Once the solicited node multicast address is created, you can generate the corresponding multicast Ethernet MAC address by adding 3333, right, to the lowermost 32 bits. So if you know the unicast MAC address of any IPv6 node, you know what is the solicited node multicast address of that IPv6 node, because this there is a standard prefix used to generate the solicited node multicast address. Anycast we already talked about, so it's like one to one of many, primarily used for locating different services. It doesn't really scale well in the internet world. Routers will have to need to be explicitly configured to route the Anycast address space, because Anycast address is by default not distinguishable from a unicast address. Right now we know that as far as the global unicast addresses are concerned, the first 3 bits are 001. So it starts with 2001 colon /3. So actually it can be either 2 or 3, right? Because depending upon what is the 4th bit. After 001 it can be either 0 or 1, right? Depending on that it will be 2 or 3. And then different regional registries or network information centers are getting assigned with multiple prefixes ranging anywhere from /12 to /23. Typically ISPs get assigned with /32 prefixes. So the ISPs, depending upon the size of the ISP, they could be requesting multiple /32 prefixes. What the ISPs would do is, ISPs assign the enterprises, right, and other customers in turn /48 prefixes. Again, depending upon the size of the enterprise, one enterprise could be asking for multiple /48 addresses. Even if you get a /48 address, if you look at the network ID portion, which is 64 bits, still you have 16 bits to do additional subnetting, right, in your organization. And how do we typically generate this 64-bit interface identifier? There are different ways this 64-bit interface identifier can be generated once you know the 64-bit network ID portion. One is by manually assigning it, which would be the case for service providers who typically support residential customers and assign the addresses using the DHCP-v6 mechanism. Or there is an automatic method to generate the 64-bit interface identifier. It is called EUI64 format. In EUI64 format, the interface ID portion of an IPv6 address can be generated from the MAC address of the node. We will see, I think, in the next slide how the EUI64 format can be used to generate the interface ID portion. And another method is to auto-generate the interface ID portion by using some kind of mechanism to generate a pseudo-random number. This is primarily to address some privacy concerns, because EUI64 format is a standard format which automatically generates an IPv6 interface ID portion from a MAC address of a node. So if you know the MAC address of any system, you know what would be the EUI64 interface ID for that particular system. So if there are some privacy concerns, then you may want to employ some kind of mechanism where some random numbers would be generated for the 64-bit interface identifier field. It is called pseudo-random because they use some mechanisms to make sure that the possibility of collisions are minimized. And as I mentioned earlier, this can be assigned via DHCP, or it can be either manually configured as well. When you are defining the IPv6 addresses like IPv4 on the routers as well as the end stations, you have the option to manually define the full 128-bit address as well. This is how you generate the interface identifier by making use of the MAC address. We have a 48-bit MAC address, and in EUI64 format, a 16-bit constant is inserted in the middle of this 48-bit MAC address. The value FFFE is inserted in the middle of this 48-bit MAC address, thereby giving a 64-bit identifier. Finally, for you to use it with an IPv6 address, you need to flip the universal local bit. If it is 0, it would be changed to 1. If it is 1, it will be changed to 0. So you already have the IPv6 prefix, right? The assumption is a node somehow came to know what is the IPv6 prefix, 64-bit prefix it needs to use. Then it needs to build the 64-bit interface identifier to build the total 128-bit address, right? So it can always auto-generate the address by making use of the EUI64 format. This is particularly helpful for some automatic address assignment mechanisms, which we will see later. There is an Ethernet type field defined for IPv6 to differentiate it from other layer 3 protocols. It is 86DD, and we know that for IPv4 it is 0800. Now, let's move on to ICMP-v6 and neighbor discovery. Any questions so far? Am I talking too fast? Do I have to slow down a little bit? Okay, so ICMP-v6 is the counterpart of ICMP-v4, what we have in the IPv4 world. ICMP-v6 in IPv6 world supports all the similar functionalities, right? The error messages and informational messages which used to be generated by the ICMP-v4, such as destination unreachable, packet too big, right, helped in path empty discovery, time exceeded if the TTL value reaches 1, right, the parameter problem if it doesn't understand some of the options defined in any of the headers, or even for the basic ping mechanism we have by making use of the echo request and the echo reply, right? All these informational messages and the error messages are supported by ICMP-v6. However, in addition to that, ICMP-v6 supports a few more functions. One is the neighbor discovery mechanism. As you may have heard, ARP is no longer supported in IPv6. But we do know that there should be some mechanism out there to resolve the link layer MAC address of a destination, because just by knowing the the IPv6 address of a destination, right, you wouldn't be able to communicate. You need to have a mechanism to find out the corresponding link layer MAC address, right? So in order to find out the link layer MAC address for an IPv6 address, there is something called a neighbor discovery mechanism defined, which is part of the ICMP-v6, which replaces the ARP which we used to have in IPv4. Also, the IGMP-v6 or Internet Group Management Protocol, which was out there in IPv4 for multicast control messaging, is also covered by ICMP-v6. The equivalent of IGMP-v4 in IPv6 is called Multicast Listener Discovery Protocol, and Multicast Listener Discovery or MLD is now part of ICMP-v6. Now moving on to neighbor discovery, it replaces the ARP as I mentioned earlier, and also it assists with the router discovery and finding out some of the parameters from the router, which will help with the automatic address assignment. It can be used to find out the reachability and unreachability of the neighbors, and also it is helpful for duplicate address detection. All of this we will see in detail soon. There are 5 neighbor discovery messages out there. Router solicitation, which is typically sent out by a booting node trying to discover one or more routers, requesting a router to send a router advertisement back with the relevant parameters. Router advertisement messages are periodically generated by the routers to the links connected to it. However, a router advertisement message can be generated in response to a router solicitation message also. Then you have the neighbor solicitation message, which is used for link layer address resolution as well as the duplicate address detection. And in response to the neighbor solicitation message, a neighbor advertisement message will be sent out. And then the router redirect messages are used primarily to inform a node that there is a better route available corresponding to a destination than the default route itself. Now let us take a look at the router solicitation and the router advertisement. As I mentioned, the router advertisement messages are generated periodically by the router. However, a router advertisement message can be generated in response to a router solicitation message also. What a booting IPv6 node would do is, instead of waiting for the next RA message to come out, depending upon the interval defined here, it will right away send a router solicitation message. And the router solicitation messages are always sent to the link local multicast destination address corresponding to the all routers, because the booting IPv6 node doesn't have any idea about what is the unicast IPv6 address of one or more routers connected to the link, right? It is trying to discover the routers themselves. So the router solicitation messages always are sent out to the all routers multicast address, which has got the link local scope, as you can see here. And the source would be the link local unicast address of the routing node. So that is one thing to highlight here. So the link local addresses are not used typically for normal communications between IPv6 nodes. Even though the applications can talk to each other even by using the link local addresses as long as they are in the same subnet or same link or layer 2 data link layer domain, the link local addresses are used primarily for the control message exchanges in the IPv6 implementation, such as router solicitation, neighbor solicitation, etc. And in this case, the booting node can automatically build a link local address if it has been configured to do so. Because we do know that the FE80 :/10 prefix is the well-known prefix which is used to build a link local address. And if the node has got an IPv6 stack which can do the EOI64, right, format for interface identifier, the full length link local address can be built by using the prefix and by making use of the MAC address. In this example here, for the sake of simplicity, we are using the address FE80 :/, FE80 :1, just as if it has been manually configured. But in a typical implementation, end IPv6 nodes would be automatically generating the link local address, and it won't be as simple as it looks here. But you don't have to be worried about it, right? Because it's automatically used. You don't have to specify those link local addresses anywhere, except for some routing protocol configuration, which we will see tomorrow. Now, in response to the IPv6 router solicitation message or unsolicited periodically, the router advertisement messages would be sent out. The router advertisement messages would have a destination address of all nodes multicast address FF02 :1. This represents all the nodes connected to a specific link, and as you can see, it has got the link local scope. So every single node connected to that link would receive the router advertisement messages. Router advertisement messages again originates from the router with the source address, which is the link local source IPv6 address of the router. So every time neighbor discovery messages or router discovery and router advertisement messages are sent, the link local addresses would be used. And typically the router advertisement message would have the data section with multiple options. It can be used to advertise multiple prefixes. What is the advantage of advertising the prefixes, right? Global unicast prefixes corresponding to the link. It helps in automatic address assignment for the nodes, if at all the router has been configured to do it. So there are certain flags set on the router advertisement message which tells the nodes connected to that particular link whether it can use automatic address assignment something called stateless address auto configuration, or it has to go with DHCP-v6. Now let us take a look at neighbor solicitation and advertisement. In this case, IPv6 nodes A and B are connected to the same data link, right, network. A knows the IPv6 unicast address of B. So A wants to communicate to B. However, A does not know the the MAC address of B. So there should be a mechanism to find out the MAC address of B so that the IPv6 address will have to be eventually encapsulated into a link layer protocol header, right, such as Ethernet. So in this case, A, which already has the IPv6 address of B, would send a neighbor solicitation message. In the neighbor solicitation message, the source address would be the IPv6 address of A. It can be either a link local address or a global address itself. And the destination address would be the solicited node multicast of B. I have mentioned earlier that if you know a unicast IPv6 address, regardless of whether it is a link local unicast IPv6 address or global unicast IPv6 address, anybody can automatically generate a solicited node multicast address corresponding to the unicast address, right? Because you are using a constant prefix and mapping the lowermost 24 bits from the unicast address to the solicited node multicast address to generate the 128-bit solicited node multicast address. So because of the fact that A knows the unicast address of B, it knows the solicited node multicast address of B as well. So A sends an IPv6 neighbor solicitation message with source IPv6 address as the address of A, and destination address as solicited node multicast address of B. And in the data portion of the neighbor solicitation, it would include the link layer address of A. And the query is, it is asking what is the link address of B. Now, what is the advantage of using solicited node multicast address, right? Instead of using an all nodes multicast address. Because we do know that this particular neighbor solicitation message needs only to go to B. Even though A does not know the MAC address of B yet, it knows the solicited node multicast address of B. And the B, as soon as it has got an IPv6 unicast address assigned, any node will generate its own solicited node multicast address and will tune into that in the receiving mode. So anybody sends anything to that solicited node multicast address would be received by the node which has got the corresponding unicast address. What that means is, corresponding to the solicited node multicast address, because it is like any other multicast address, right? There is a MAC address which would be created by making use of the lowermost 32 bits and then adding the 33 constant, right? So any node is tuned into its own solicited node multicast address as well as the Ethernet MAC address, right, at the data link layer corresponding to the solicited node multicast address. So because of that, even though A does not know the MAC address of B yet, this particular message will be received and processed only by B, which is entirely different from what we used to have in the IPv4 world of ARP mechanism, right? Because ARP is always a broadcast. Even though only one node is going to respond back, every single node in the network link layer needs to process it. However, in this case, it is entirely different. By means of using the solicited node multicast address, it can always be addressed to the destination node. And as soon as B receives the solicited node multicast, as soon as B receives the neighbor solicitation message, which was sent out by A, what B is going to do is, B will send a neighbor advertisement message, which would be a unicast message, back to A. As you can see, the source address at the IPv6 layer is B, the destination address is A, and the data portion for the neighbor advertisement message would be the link layer address of B. Now A has got the MAC address of B, and B has received the MAC address of A from the original message, and they can have the normal unit communication. This is another function supported by the neighbor solicitation in neighbor advertisement messages. Regardless of the mechanism which is used to assign an IPv6 address to a node, which we will see different mechanisms later, right? A node, when it gets assigned with an IPv6 address, it keeps the address or treats the address as a tentative address, because it wants to make sure that nobody else in this particular data link layer network is using that particular address, right? So in order to check whether the tentative IP address which it has got is in use by one or more nodes in the network, it sends a neighbor solicitation message, which is a special neighbor solicitation message. Here, as you can see, for this neighbor solicitation message in the IPv6 header, the source address is : which represents the unspecified address. The reason being, the IP address which is assigned to host A is still in the tentative state. It doesn't know yet whether somebody else is using it. The destination address is a solicited node multicast address which is built from this tentative address. The reason being, if by any chance this tentative IP address which was received by host A has already been assigned to somebody else, that station would be tuned into this solicited node multicast address, right? So once this neighbor solicitation message is sent out, in the target address or the data field, it just lists down the address itself. If by any chance there is another node, in the unlikely event that there is a different system using due to some misconfiguration from the administrator side, the exact same address, that node is going to receive the neighbor solicitation message because he was tuned into the solicited node multicast address corresponding to the tentative IP address, which is a regular IP address for host B in this case, right? And host B will find out that there is another host which is trying to make use of the address which has already been assigned and in use by host B. So host B will send a response back. In this case, the response would be going out to all nodes multicast address. The reason being, host A hasn't implemented this IP address yet, which is in the tentative state. Because of that, host A would not be listening to the solicited node multicast address corresponding to this, right? And it cannot be because somebody else is using it. So the response is going back to an all nodes multicast address, and that will inform host A that there is a duplicate address in the network. Now moving on to router redirect, the concept is quite simple and straightforward. In this case, R2 is the default router. Station A wants to send some IPv6 packets to a destination IP address, and because R2 is the default router, it sends them to R2. However, R2 knows that R1 is the better route to reach that particular destination subnet from the same data link layer. So R2 would send a router redirect message, which would be a unicast message going back to the node A, and will inform the node A that for this particular destination subnet here, make use of R1 as the next hop instead of R2. Now moving on to auto configuration. Auto configuration can be implemented by making use of the router advertisement messages sent out periodically by the routers connected to a data link network. In the router advertisement message, the router have got the option to list down one or more prefixes, IPv6 global prefixes corresponding to the data link layer. And each of these prefixes can be associated with a valid lifetime and a preferred lifetime. So depending upon the settings in the router advertisement message, there are a few flags out there. One of the flags is called managed address configuration flag. So if that flag is set to 0, it tells the nodes connected to that particular data link layer that the nodes can undergo stateless address auto configuration and can make use of the prefixes, one of the prefixes advertised by the router in the array, and combine that prefix and add the interface ID portion by making use of the EUI64 format to build the 128-bit address. So that way, without the involvement of a DHCP v6 server, the nodes can automatically get assigned with the IPv6 address. In fact, valid IPv6 addresses. It makes the IPv6 address assignment plug and play. And it helps with renumbering also. As I mentioned, all the prefixes, right? If the router is sending multiple prefixes, it has got the option to define different values for preferred and valid lifetimes. So depending upon the values defined for the preferred and valid lifetimes, if a host has been configured with one prefix, and if the router sends an advertisement with another prefix which has got a better preferred lifetime value, right, it is going to reconfigure and then move the network, it will eventually move the network to the new prefix. So the auto configuration, I think renumbering also can be automated by means of using the router advertisement messages. As I mentioned, the equivalent of IGMP in IPv4 is multicast listener discovery, which is also supported by the ICMP v6. MLD has got two different versions, MLD version 1 and version 2. MLD version 1 is equivalent to IGMP v2, which supports any source multicast, and MLD v2 is equivalent to IGMP v3, which supports source-specific multicast. And similar to IGMP snooping, which is implemented by the switches, there is something called MLD snooping also. The functionality is very, very similar. The data link layer switches which will do the MLD snooping similar to IGMP snooping in order to support the efficient distribution of multicast packets. In this case here, it is showing a couple of hosts joining a particular IPv6 multicast group, right, by sending the report message, MLD report message, H1 as well as H2. And as soon as the router receives the very first report message from one of the nodes, it's going to start streaming the multicast packets into that particular network. And if somebody leaves by sending a done message, obviously the router is going to send a source specific query to check whether there are any other nodes which is interested in that particular multicast group, and if there is at least one node which wants to continue receiving packets into a multicast group, then it would respond back for that source specific group specific query. So these things we already discussed in the previous slide. Any questions so far? Just to take a high-level look at DNS, we have similar to the IPv4 DNS support, DNS is supported in IPv6 also, but it has to be implemented based upon all the different RFCs out there defined to support IPv6 as well. And in IPv4, the IPv4 addresses are referred to as A records, and in IPv6 it is referred to as a quad A record. And then pointer for reverse lookup is also out there for IPv6 as well. And one thing to keep in mind is the DNS could be using an IPv4 application. It can use TCP or UDP, and it could be, regardless of whether it is running on IPv4 or IPv6, it can be requesting a record as well as quad A record. So the underlying transport for the DNS query could be IPv4 based transport, but a client could be requesting a quad A address. Likewise, the underlying transport can be an IPv6 based transport, and a client could be requesting a address or IPv4 address. So this is an example which shows corresponding to a host name, you have an A record and a quad A record. In some cases, it can request for A as well as quad A record corresponding to an FQDN, and both can be returned if that particular address is supported by IPv4 and IPv6. And the pointers are for the reverse lookup, and there is a slight difference here. It uses hexadecimal but in dotted format, not in colon format, and in the reverse order. Now, moving on to the final section here, the DHCP-v6. As far as IPv6 address assignment is concerned, these are the different methods available. One is manual assignment, which is quite straightforward, right? So you are configuring the addresses manually, whether it is a router or end station. Then you have the stateless address auto configuration, which we already discussed to some extent when we covered the neighbor discovery section and the router advertisements, right? And then there are two types of DHCP, stateless DHCP-v6 and stateful DHCP-v6. And DHCP-v6 finally supports something called prefix delegation, which is helpful to support these residential customers who wants to have a prefix instead of a 128-bit address, and in turn do the address assignment locally, or a small business customer who wants to receive a prefix via DHCP-v6 for the local router, customer premises router, and implement some mechanism to assign the addresses locally to the nodes connected to that network. Stateless address auto configuration is basically implemented by making use of the router advertisement messages. In the router advertisement message, there is a flag called managed address configuration flag, and if that flag is set to 0, that indicates that all the nodes, IPv6 nodes connected to that particular network can do this stateless address auto configuration. And for it to work, the router should include at least one prefix in its router advertisement message. Because the way the stateless address auto configuration works is you make use of the prefix advertised by the router and then build the interface ID portion from the MAC address by using the UI64 format to come up with the 128-bit address. Now, why would you want to go for DHCP v6 when stateless address auto configuration is supported? The primary reason being the stateless address auto configuration does not give you a mechanism to track the IPv6 addresses assigned to different nodes. There is no binding information available between a node and the IPv6 address because the addresses are assigned automatically, right? And this is particularly important in the case of service providers for billing purposes, for lawful intercept whatsoever. They need to know who is using what address, right, in terms of their customers, the end subscribers. The stateless address auto configuration may only work in limited deployment scenarios for enterprise networks, right? But when it comes to service providers, they need to know who is getting assigned with what address so that they can support the management of their subscribers. Now, moving on to stateless DHCP v6, we have seen that we can automate the address assignment process by making use of the router advertisement messages without a DHCP v6, without the involvement of a DHCP v6 server. However, after you get the address, if you really want to communicate with the rest of the network, you need to find out a few additional configuration parameters such as the list of name servers or DNS servers which you need to use for the name to address resolution, right, or other configuration information. So in order to receive those configuration details, one mechanism would be to manually configure those on the individual nodes, which is not going to scale. And an alternative available out there is you can use the stateless address auto configuration for address assignment portion, and in order to receive the other auto configuration information such as the list of name servers, the domain name, etc., the node can still make use of the DHCP v6. The advantage is the number of DHCP message transactions, right, going back and forth between the client node and the server has gone down drastically. The processing overhead on the DHCP v6 server has gone down, but because of the fact that we want to automate the process of assigning the list of name servers, the domain name and other relevant implementation specific configuration parameters, you can use the DHCP v6 server still for providing other configuration information. And there is a second flag in the router advertisement message called OBIT. That flag tells the nodes that the other configuration information can be received by using a DHCP v6 server. So M-bit or M flag in the router advertisement message can be set to 0, indicating it can use the automatic address assignment, and O-bit would be set to 1, indicating that the other configuration information can still be received from a DHCP v6 server. And this is how the mechanism works. You have a DHCP v6 client connected to a local network here, and the router advertisement messages are periodically sent out by the router connected to that data link layer network. And in the router advertisement message, EM bit was set to 0, and because of that, the client was able to assign itself an IPv6 address automatically. However, as you can see, the O bit or other configuration bit is set, indicating that DHCP v6 mechanism is supported for receiving the other configuration information. So once the address assignment has been completed, including the duplicate address detection check, the client can send an information request to the DHCP v6 server. It would typically be going out to a multicast address because the client doesn't know the DHCP v6 server's address. There are multicast addresses defined for that. And then the DHCP v6 server, if configured properly, would send a reply back with the requested configuration information, such as most common one would be the list of name servers, the domain name, etc. Now moving on to stateful DHCP v6. In stateful DHCP v6, as the name implies, the IPv6 address assignment is also done by the DHCP v6. So there is no concept of stateless address auto configuration. Stateful DHCP v6 can be implemented in two ways. One, in the router advertisement message, the managed address configuration flag can be set to 1 to indicate that all the nodes connected to that particular link where the router advertisement messages are seen should undergo the stateful DHCP v6. And another option is when you configure the client, such as Windows 7 machine or Apple computer or whatever, you can specify that the system needs to undergo the DHCP v6 for address acquisition. Let's take a look at the stateful DHCP v6 address allocation mechanism and the relevant messages involved. In this case, in this particular example, the DHCP v6 server and the client resides on the same data link layer network, which is extremely uncommon anyway. So as you can see, first of all, the DHCP v6 client would inspect the contents of the router advertisement message, which says that managed bit is set, and because of that it has to undergo the DHCP v6, and the client would send a DHCP v6 solicit message towards the DHCP v6 server. It does not know the unicast IPv6 address of the DHCP v6 server, but it will be going out to a couple of one of the multicast addresses defined for the DHCP v6 servers. And then in response to the solicit message, DHCP v6 server will provide an advertised message back to the client, and the advertised message will tell that the server can assign an IPv6 address, and typically in the advertised message it would include the IPv6 address the DHCP v6 server is willing to assign, and also any other additional configuration information requested, right? And if the DHCP v6 client is happy with the advertise, it is going to send a request message, and for the request message it will get a reply back from the DHCP v6 server, and the address assignment will complete. So in this case, the IPv6 address as well as the other configuration information will be received during this single DHCP v6 transaction. Just some comparison between stateless DHCP v6 and stateful DHCP v6. As the name implies, the stateless DHCP v6 does not provide you any mechanism to find out the association between a node and an IPv6 address. However, the stateful DHCP v6 gives the state information or binding information, and it periodically refreshes the addressing also, right? And another thing to highlight here is the prefix delegation, which I mentioned earlier, which is used to assign the prefixes, right? Not the 128-bit address itself, prefixes to home routers or the local customer routers, so that the customer router can in turn assign the addresses to the local network. That is supported only via stateful DHCP v6 mechanism, obviously. And just list down the some of the messages. We have already seen these messages: solicit, request, confirm, renew, rebind. Some of them we have seen, not all of them, but we have a better explanation of these messages in the next slide. And one thing to highlight here is, we do know that in most of the implementations there are DHCP v6 relay agents involved, right? Which for the sake of scalability, because typically you would not have a DHCP v6 server in the same network as the client. So the relay agents, in the case of DHCP v4 mechanism, simply will take, for example, the discover message and forward it to the configured relay agent. However, in the case of DHCP v6, the relay agent will pick up the client message and encapsulate into a different message, because there is another message defined for sending the information from the relay agent to the server. So the relay agent, if it receives a solicit message, will encapsulate that solicit message into something called a relay forwarder message. So and it will add any additional options, such as DHCP v4 relay agent options we have, right? So any additional options the agent wants to include will be included in the relay forwarder message. And if relay agent is involved, the advertised message, which is supposed to come back, right, for the client, actually would be encapsulated in a relay reply message. And there would be option responses corresponding to the original options requested by the relay agent. And after the relay agent releases the relay reply, it can extract the actual client message and send it back towards the client. And this is just a format of the relay message, relay forwarder and relay reply. Basically, it will include the link IPv6 address of the relay's interface from which the packet, client-side packet came in, and also the IPv6 address to which the response needs to come back. So this is there are more comparisons coming in. So as far as the addressing is concerned, for the source address, we know that in the case of DHCP v4, we always use the all zero address to indicate that the node has not been assigned with an address, right? But in the case of DHCP v6, every single node is supposed to be assigning itself a link local address by making use of the FEAT ::/10 prefix, right? So the source address for DHCP v6 messages would always be link local unicast address. And as far as the destination address is concerned, it would be a multicast address. And there are two types of multicast address. One is all DHCP v6 servers and the relay agents multicast address, and which has got a link local scope. And the second multicast address is an all DHCP v6 servers multicast address, which has got a sites local scope. However, the client will always use the link local scope multicast address, which can be picked up by either a DHCP v6 server, if at all there is a DHCP v6 server on the same subnet, or it will be picked up by a relay agent. And the use of the site local multicast address is out there for the relay agent to forward the relay messages to multiple DHCP v6 servers, if that is any intended behavior. But typical implementations would have unicast address for the DHCP v6 servers defined on the relay agent, so that relay agent, upon receiving the client's request, can encapsulate those messages and forward directly to the configured DHCP v6 server. This is a side-by-side comparison between the message types. If you are familiar with DHCP v4, we know that the very first message which comes out in the DHCP v4 world is DHCP v4 DHCP discover. The equivalent of DHCP discover is solicit. Equivalent of DHCP offer is advertise. And the equivalent of DHCP request is either request, renew, or rebind. Renew is for renewing the IPv6 address when it is about to expire. But the difference, and the rebind also is used for renewal, but the difference between renew and rebind is renew goes to the original DHCP v6 server which assigned the address, but rebind goes as a multicast to all DHCP v6 servers, primarily because it did not get a response back for the renew. And DHCP acknowledgement and no acknowledgement if there is some failure from the server side. The equivalent one is reply in IPv6, and DHCP release has retained pretty much the same name for the message. And DHCP inform was out there to collect the other configuration information. similar to that what we have here is information request, and the decline can happen if at all the client doesn't like some of the parameters offered by the server, or it can happen if the duplicate address detection fails, which is very, very unlikely. And the confirm message will be generated by a DHCP v6 client just in case it detects some kind of network level changes. For example, if the client is regularly listening into the router advertisement packets, and if it finds that, okay, the prefixes advertised by the router has changed, right? So it can just send a confirm message back to the DHCP v6 server to make sure that the address is still valid. And the reconfigure message would be typically generated by would always be generated by the DHCP v6 server if the administrator triggered reconfiguration happens. If something has changed in terms of the address copying on the server side, this can be sent to trigger a renewal. And relay forwarder and relay reply, as we have seen earlier, is used for the relay agent encapsulation of the client side messages and de-encapsulation of the server side messages. So to summarize, we have seen stateful DHCP v6, which takes care of address assignment as well as other configuration assignment. Then stateless DHCP v6, where address assignment happens through stateless address auto configuration, but the other configuration information is received through the DHCP v6 again, and then Slack, which we covered, which is used only for the address assignment. And moving on to DHCP v6 relay agent, I know that we already touched upon the relay agent. This is primarily used for scalability because we cannot have a DHCP v6 server in every single network, right? So you need to have relay agents out there implemented for scaling the DHCP v6 service. And we have already seen that the implementation is slightly different. Instead of simply forwarding the packets by adding some options, it encapsulates in an altogether different message. And this shows the role of the relay agent. When a client-side request comes in, what the relay agent is going to do is encapsulate that into a relay forwarder message and send it to the server. And the server will have the reply for the client, which is again encapsulated in a relay reply message, which comes back as a unicast message down to the relay agent. Relay agent, upon receiving, will extract the message meant for the client and send it back to the client. Now, moving on to prefix delegation. Prefix delegation also can be implemented by DHCP v6, and a typical example is our internet service providers such as cable operators who wants to assign a prefix for, right? And if you think about it, in the IPv4 world, we do know that we have multiple systems out there today, typically in any home if you think about it, right? However, in IPv4 we use NAT. Right, Comcast or Time Warner Cable or whoever is assigning an address assign one global IPv4 address, but you have some NATing device out there which takes care of assigning private address space to your multiple nodes connected in your home network, and all of them can browse the internet, right? But in IPv6, the very idea behind having IPv6 is just to, get away from NAT and all the workarounds which we have in place to address the shortage of address space. In IPv6, what the providers would typically do is, instead of assigning 128-bit addresses separately for the nodes connected at one customer premise, which can also be done, it will assign, it has got the option to assign a prefix like /48 or /56 or even /64-bit prefix to a customer router. As long as the customer side router is capable of doing DHCP v6 and use the prefix delegation option in DHCP v6 to request for a prefix. And customer router, once it receives the prefix, can locally implement some kind of address assignment mechanism. It can be stateless address auto configuration, or it can be DHCP v6. some lightweight DHCP-v6 running on the customer router to assign the addresses to the local systems. And that is how, when we all move to IPv6, prefix delegation would be the way to go for, even for home subscriber addressing. And this is an example which shows the prefix delegation process. If you look at the DHCP-v6 messages, we are using the exact same set of messages. However, the difference is some of the settings in the messages, right, will specify that it is asking for a prefix instead of a 128-bit address. In fact, you can request a 128-bit address as well as a prefix, both one or more prefixes, by using a single DHCP-v6 message as well. So the DHCP-v6 transaction is similar to that of a 128-bit address assignment, but in this case, it's a prefix assignment. And this is a prefix delegation message exchange with the where a DHCP-v6 relay agent is involved. And typically, we would have relay agents involved because otherwise the solution is not going to scale. And then obviously, you would make use of the relay forwarder and relay reply messages, right? And one thing to keep in mind is the edge routers, right, will have to dynamically add those prefixes into the routing table. The way it does is, the edge routers, since they are acting as the DHCP-v6 relay agent as well, they would come to know which are the prefixes getting assigned to different clients connected to the access network. So they would dynamically add those routes corresponding to those prefixes, typically as dynamic static routes, and then you would have to have a configuration in place to inject those static routes into a dynamic routing protocol so that in your service provider's routing table, these dynamically assigned prefixes also would be available. That completes the session for today. Any questions from any of the sections which we have covered? I'll be continuing with the rest of the sections, primarily the IPv6 routing protocols and some major translation mechanisms tomorrow at 4 o'clock here in the same room. Hope today it was helpful and looking forward to see you guys tomorrow. Thank you.